Welcome. Today we are discussing Module 7.2, Building a Full End-to-End RAG Script, Practical. Here is a quick look at where we are in our curriculum. Hello and welcome back. Today, we are moving away from toy examples and building a fully operational, production-ready, end-to-end RAG script. As you can see from our system blueprint on the screen, a real-world RAG system requires a clean, sequential flow, starting from raw document ingestion, moving to deterministic chunking, proceeding to a specialized vector database store, and finally routing queries through precise context synthesis before invoking the LLM. In this lecture, we'll build this exact flow step by step. Remember to check the link in the description to download the architecture diagram and script so you can follow along as we code. Let's dive into the code. First, we establish our imports and initialize the underlying infrastructure. We're using standard, production-grade Python packages. We load our environment variables using dotenv. Initialize ChromaDB as a local persistent storage system so that our indexed documents aren't lost when the process terminates, and construct the OpenAI client wrapper. Please check the link in the description to download the architecture diagram and script to run this directly on your local machine. Well, isn't that just perfect timing? It looks like we've stumbled upon our very first live debugging moment, right as we're getting started. This module not found error. No module named chromab is a classic example of a missing dependency. Python is telling us it can't find the chromab library, which our script needs to interact with our vector database. It's a fantastic teaching point, actually. To fix this, we simply need to open our terminal and execute pip install chromab. Once that's done, we can rerun the script. Then, we should finally see those clean logs indicating our environment variables are loaded and, more importantly, that our SQLite-backed Chroma database is ready to accept operations. This persistent vector directory is key to ensuring we can seamlessly read and write embeddings across multiple runtime sessions without needing to rebuild everything from scratch. Now, let's write our ingestion engine. Standard string splitting breaks sentences in half, causing catastrophic loss of context. To prevent this, we employ LangChain's recursive character text splitter. It intelligently splits based on paragraphs, sentences, and finally individual characters. We then load these chunks directly into our persistent Chroma collection. Remember, the full code package can be downloaded via the link in the description. Whoops! Looks like we've hit a live debugging moment, which is actually a fantastic opportunity to address a common issue. Our traceback clearly shows a module not found error, no module named LangChain. This simply means the LangChain library, crucial for our text splitting, hasn't been installed in our environment yet. No problem at all. A quick pip install LangChain in the terminal will resolve this. This is a great reminder that managing dependencies is a fundamental part of software engineering. Once that's done, we can proceed to see how our ingestion function splits the company knowledge base document into clean, overlapping fragments, and how Chroma automatically indexes them, assigning structured metadata to our source files. With documents indexed, we write our retrieval helper function. Given a user query, this function queries the Chroma collection. Chroma automatically vectorizes the raw question string behind the scenes and performs a semantic search to return the top 3 most contextually relevant document segments. This ensures we are only passing highly relevant content to the LLM. Go ahead and download the source code via the link in the description to see how these search metrics are computed. Here we run our retrieval function with a specific query about remote work regulations. In the output window, you can see how the backend system performs search matching and extracts only the relevant text passages directly associated with remote work hours. This significantly reduces our LLM token costs. Now for the final component, LLM reasoning and response generation. We design our generation routine with strict instructions. The system prompt commands the model to act as a focused assistant, relying exclusively on the provided context. If the answer isn't in the provided text, it must declare that it doesn't know, rather than making up answers. Be sure to check the link in the description to download the architecture diagram and this full Python script to start running safe, non-hallucinating AI pipelines. Let's run the completed end-to-end RAG script in our terminal. As we run the unified script, the system parses the document, matches our query on remote work, pulls the exact source passages, and outputs a highly professional, verified response in seconds. Building a solid script is a major step, but how do we scientifically prove that our retrieval is accurate and our responses are factual? In our upcoming lecture, Module 8.1, Evaluating RAG Pipelines with RAGs, Theory, I will guide you through the mathematics of automated RAG validation, exploring context recall, precision, and faithfulness metrics. Don't forget to download the code and diagram from the description, subscribe, and I'll see you in the next class.